Hello everyone, this video will show how to graph rational function in transformed form and how to change a rational function in transformed form to its equivalent standard quotient form. Now let's go over this first example. Looking at this example that we have here, we can go ahead and tell the locator point HK from here, and that would be positive 3, negative 2. So I'm going to go ahead and write that down here. So the locator point is on 3, negative 2. So I'm going to go ahead and label that up here. This locator point is the intersection of both the vertical and the horizontal asymptotes. We can go ahead and say that the equation for the horizontal asymptote would be y equals, it touches on negative 2, and the vertical asymptote is, the equation for that would be x equals, and it's touching on the x-axis at 3. So we go ahead and sketch the graph here. Since our a here is positive 1, it tells us that the graph goes this way, and this other branch is going to go this way. And we're going to draw the other branch as well down below. So this is the shape of the graph. Now let's determine the left end behavior and the right end behavior of this graph. So looking at the left end behavior of the graph is going toward negative infinity. And at the same time, it's approaching the asymptote, which is negative 2. So we go ahead and write that as x approaches negative infinity. F of x, or the y, is going to approach towards its asymptote, which is negative 2. Now let's write the right end behavior of this graph. So for the right end, the graph goes towards positive infinity to the right. And at the same time, it is approaching towards the asymptote, which is located on negative 2. So we can go ahead and write that as x approaches positive infinity, f of x approaches negative 2. Now let's determine the domain and range for this graph. So the domain for this graph would be all real numbers except the one on the vertical asymptote. So we can take this vertical asymptote as a wall that the graph can't cross. So we go ahead and write the domain right here. So the domain would be all real numbers except 3. Now let's look at the range. So for the range here, the graph goes all the way to negative infinity. It goes all the way to positive infinity, but it cannot cross the horizontal asymptote, which is located on negative 2. So we can go ahead and write the range as all real numbers. So this is the mathematical symbol for all real numbers, and that is except negative 2. Now it says in the problem that we're supposed to transform this to its equivalent standard quotient form. So what are we going to do with this equation is that we're going to subtract them together. Now notice that their denominators are not the same because this expression right here can be written as, so that 2 has an invisible denominator of 1. So that we can subtract them together, we have to make sure that their denominators are the same. So that tells us that we are going to multiply the second term here, which is 2 over 1, with the denominator of the first, which we will have this as our giant one. So we're going to multiply this x minus 3 over x minus 3 to both numerator and denominator. So what are we doing right now is we're not changing the whole expression because we are just multiplying 1 to the whole expression. So we go ahead and simplify this. If you notice, they already have the same denominator. So we can take their common denominator, which is x minus 3, and then we're going to join them together. That is 1 minus 2 times x minus 3. So we can go ahead and distribute 2 to each of the terms inside the parentheses. Now we can combine like terms. So the like terms that we have here would be 1 and 6. So this comes out negative 2x plus 7 over x minus 3. So this is the equivalent standard quotient form of this given function that we have up there. So these two are equivalent to each other. Now let's have another example. Looking at this example, our locator point is at -2, +3. So I'm going to go ahead and write that up here. So I'm going to go ahead and draw the graph here. So it's -2, +3. So it's going to be up here. And we're going to draw the asymptotes. Since we see that this one here is a negative, the graph flips along the y-axis. So that means the side that we get here is going to go to this side, and the other would go that way, and then it's going to flip on the other side as well. So this is the graph of this given function that we have here. From here, we can go ahead and say that our vertical asymptote is located at x equals -2, and our horizontal asymptote is located on y equals 3. So I'm going to go ahead and write that up here. Now let's go ahead and write the left-hand behavior and the right-hand behavior of this graph. So for the right end, the graph goes towards -infinity, and it approaches towards its asymptote located at 3. So we can go ahead and say that as x approaches -infinity, that's to the left, f of x approaches towards 3. On the other hand, this graph here on the right end of the graph is going to go towards +infinity, and it's approaching the asymptote 3. So we can go ahead and write as x approaches +infinity, f of x approaches 3. Now let's determine the domain for this graph. So this graph will have a domain of all real numbers going from left to right of -2, but it cannot cross -2. So we can go ahead and say it's going to be all real numbers except -2. Now for the range, the graph can go up infinitely and can go down infinitely, but it cannot cross on 3. So we can go ahead and say that the range would be all real numbers except 3. Now let's change this given function that we have here to its equivalent standard quotient form. So what we do here is that we are going to rewrite this. So please remember that this 3 has an invisible denominator of 1. We want their denominators the same. So we're going to go ahead and multiply giant 1 to this in a form of x plus 2 over x plus 2. So we go ahead and simplify this. If you notice, we already have the same denominators. We can collect the denominators together, which is x plus 2. So we get a -1 plus 3x, because that's 3 times x is 3x, and then 3 times 2 is 6. So we go ahead and combine like terms. So the like terms that we have here would be, so this is, by the way, this is a 3x plus 6. So the one that we can combine would be -1 and +6. So this tells us that its equivalent expression in standard quotient form will be 3x plus 5 over x plus 2. Which means that if we graph these two functions that we have here, they match up each other because they are equivalent equations. So that is how we sketch the graph of rational function in transformed form and how we change equivalent standard quotient form.